All right, well, why don't we just start? So we're very happy to have Francesco Lin here from Princeton, and he's conveniently written his title on the board, so I can't mangle it.
A very long title.
And so he was going to tell us about involutive monopole Floer homology and Bar Natan's deformation Khovanov homology.
Okay, thank you very much for the invitation. It's been a very pleasant 2 weeks here. Okay, so before that, there are two themes that I want to talk about. I guess they're kind of in the spirit of the semester, so I'm really happy to talk about it here. So first of all, it's there's this whole study of spectral sequences from Khovanov homology to some gauge theory. Okay, so the first theme I want to talk about is spectral sequences from Khovanov homology to Floer. Okay, so this is the first theme on my talk, and the second theme is P2 symmetry in Seiberg-Witten theory. Okay, so this, I guess, become popular in the last few years because Ciprian used it to disprove the triangulation conjecture. Okay, and yeah, I guess this is a topic that I've been thinking about the last few years, and then thinking about it, I found some connection with Khovanov homology. And yeah, that's what I want to talk about. So I guess the talk will roughly go like this. So the first part will be an introduction to this, to a quick review of what these two things are. Okay, and then I want to tell you a little about the main results. The third, I want to tell you a little about why it works. And the fourth thing I want to say is why it doesn't work. Well, this of course it's conjugation, but this is in the P2 case. Right, because I don't know if you did. I usually, my talks in the title usually have P2 monopole for homology, but this time I will talk about involutive stuff. So that's why it doesn't work in that case. Okay, any question about this introduction? I'll just go. Okay, so let's start with. So how does the board work? Is it? Yes. Okay. Okay. Well, one. Okay, so 1A, 1. Okay, so I'll just quickly review what all these spectral sequences are. So, okay, so if you have a link in S3, well, in some sense, every invariant comes from Khovanov homology. That's what we learned in the last few years. So, so there are a spectral sequence from Khovanov homology of L, or some version like the reduced, like of the mirror or something, converging to, and this converges to many things. So I guess the first one that people point out was Li's theory, Li homology of L. Then there's, the Floer of the branch of the cover of the mirror. Okay, this upside down. And then, well, you can go to the monopole homology of the branch level cover. This is boom. These are more or less the same spectral sequence because these two invariants are the same, isomorphic at least. And then there's the instance on singular instance on homology by Khovanov. Okay, and well, if you're a topologist, you're interested in these kind of things because, well, there's this really cool invariant of knots, but it's unclear what it means from a topological viewpoint. And using this spectral sequence, since you can tell something. For example, well, Jake used it to provide genus bounds, visualize genus bounds. And here, this spectral sequence was used by Kramer and Morocco to show that Khovanov rejects the unknown. Okay. Yeah. Yeah, I guess recently there was this work by Baldwin, Haddon, and Andrew. And what they did is they formalized everything in a they created a general formal picture. To deal with this kind of spectral sequences, to deal with naturality and functionality of all those things. Okay, anyways, what I am most interesting about is this one. Okay, so if you're not familiar with monopole homology, you should just think of HFF. Okay, it's more like the same. Okay, so just to quickly review how that arises. So the key observations are the following. So why do you have this spectral sequence from Khovanov homology to monopole homology of the branch level cover? Well, the first key observation is that, well, what do you do in Khovanov homology? You have the link with the crossings, and then you do resolution. You'll probably get the numbers wrong. I told these are 0 and these are 1. Okay. And well, Khovanov homology is like resolving all the crossings and then associating some complex to this. Yeah. So where does the branch level cover come in? It's it goes back to this thing called Montesinos trick. Okay. In particular, sigma, the branch level cover of L0, the branch level cover of L, and the branch level cover of L1 fits in a surgery exact triangle. Okay. So this means that, well, there is a knot, for example, in the branch cover of L, such that if you do surgeries along that, you get the other two. And this knot is really easy to see, it's this knot, okay? So this, when you go to the branch level cover, it gives you a knot in the branch level cover, and if you do surgeries on that, you get the branch level cover of the other two. Okay, and the other key observation is that, in Khovanov homology, you take a projection and resolve everything until you get circles. And yeah, if you have, let's say, k plus 1 circles, and you take the branch level covers of this, well, this is just S2 times S1 connect some k times. And so the Floer homology of this is just V to the k, where V is a copy of F in degree 0, and a copy of F in degree this is in degree 0, and this is in degree -1. Okay, so this you should think of this is the V that appears in Khovanov homology, the one with the V plus and the V minus. Okay, this is a crash course in why you have this spectral sequence. Okay, so this is the first thing, and okay, I want to quickly tell you where P2 comes in. Also, any question about this part?
I have a question.
Yes, sure.
What was the degree of the second thing? So one was degree 0 and one was degree what?
-1.
Just -1?
Yeah.
Oh, okay.
Why?
I thought it said like degree, never.
No, degree -1, yeah.
Okay.
Okay. Yes. So, part 2, so I'm going to tell you a little about P2 symmetry. in Seiberg-Witten theory. So okay, the group we all care about is HM2 of Y. If you're not familiar with monopole, you should just think of this as HM plus of Y. Okay? And the really nice thing is that this decomposes along the set of spin C structures. Okay, and these are modules over f of u. And yeah, so if you think of it from the point of view of Seiberg-Witten theory, this arises because this is the homology of BS1. Okay, this is the significant. Okay, this is because the Seiberg-Witten equations have an S1 symmetry, a natural S1 symmetry. Okay. From the hierarchical point of view, it has a different interpretation, but I guess in this case, it would be nicer to have it this. But yeah, the important thing is that this set has a natural conjugation by J, conjugation action. And it's nice because, well, the Floer groups associated to conjugate spin C structures are naturally isomorphic. Okay, so but indeed this isomorphism actually, but it's not just at the level of groups, but it comes from at the chain level. Okay, so when you have an involution at the chain level, then you can do some Z2 equivariant homology. Okay, so you can do Z2 equivariant homology. And this is the same, if you think of it in the Seiberg-Witten case, this is because the important thing is that the Seiberg-Witten equation actually have a pin2 symmetry. Which is just S1, you know. Okay, so yeah, the Seiberg-Witten equation are on the nodes, they only have an S1 symmetry, but in some special cases you can find an extra symmetry coming from quaternionic involution. So yeah, you can use this extra symmetry to hook up these other groups, which is called pin2 monopole thermology. And this is split as the direct sum over the C structures. Okay. Module. So this is pairs of spin C structure conjugations. Okay. And yeah, and these are modules over. Well, you can guess instead of BS1, you will have BP2. Which is just f of q, v over qq. Sorry, I forgot to say here, this has degree plus 2, minus 2, and this has degree of q equals minus 1, and degree of v equals minus 1. Okay, so yeah, on the other hand, we want to work with something simpler. So in the Hegel-Floer case, well, HF plus it's usually harder to work with, so you usually switch to HF hat. And that's what you do is like, you take the cone of U, and you get HF hat, which is just, in the monopole case, it's called HM y tilde. Okay? In this case, well, the natural thing to cone off is V, so you can cone off V. And you get what I call HS y tilde. And well, the thing you were coning off also had an action of Q, so this thing still counts with a Q action. Okay. And yeah, I guess the topological way to think of this is the homology of RP2. Okay. Later we'll see exactly where this RP2 comes from, I guess. Questions? Okay. So yeah, I guess this is one gadget to work with. But then, okay, this is gonna be a little. We can go even further and own of Q squared 2. And so instead you can set Q squared to be 0, and you get this thing which is called involutive monopole for homology. Y tilde of y, and this is a module over f of q over q squared. And this is the one which corresponds to right? So Hendricks and Manolescu did all this involutive story in the Hagar-Floer setting, and they output the simplest version is this HMI tilde that I'm gonna talk about. Okay, so well, so to recall, like there are these three invariants that one can hook up using Seiberg-Witten theory. Well, there's the one we're all familiar with, I guess, the Y tilde version, and then there are these other versions which are more complicated and come with an action of Q also. And in one case you have Q squared equals 0, and in one case you have Q cubed equals 0. Okay. Any question about this?
That's right. Is it important that you're using F2 coefficients instead of Z coefficients?
So yeah, because so in some sense the cohomology of RP2 is more interesting with F2 coefficients.
Okay.
If you lose every ring structure if you use Z coefficients. Yeah, and also, well, yeah, and in what I'm going to talk about, yeah, this, well, the thing I'm going to talk about only works in characteristic 2 actually. So it's very important that we're using Z2 coefficients. Okay, so well, to review, we have two objects here, which is like, in one case we have all these spectral sequences starting from Khovanov homology and converging to some Floer homology invariance of the links. And on the other case, on the other side, on the other hand, we have all these Floer homological invariants which come from studying the conjugation in Seiberg-Witten. Okay, so what I've been thinking about is like, well, is there any relation between these two? And the answer is yes, and it was already there, the solution. So, okay, well, let's. Okay, so I guess the main question I have is. Part 2. So question, is there a spectral sequence from Khovanov type invariance to HMI tilde or HS tilde. Okay, so of course, well, you should think of this as more complicated version of the basic Hagar-Floer homology, and that has a spectral sequence. So I guess this is a kind of natural question to ask. And the answer is yes for this. And here it's like, well, we have a good candidate. I don't know how to prove that there's a spectral sequence. I guess it's nice that the candidate is already there, was already there. So the candidate is Bar Natan's deformation. Of Khovanov homology. And this, okay, going back to what Marcus said, this only works in characteristic 2. Okay, so yeah, so going down a little bit and going back to what Khovanov does. So Khovanov, so you start with a link. So to a link, Khovanov associates a diagram, and then from this diagram you can cook up this Khovanov chain complex. Okay, this is like the Khovanov chain complex. Coming from pixel resolution. Okay. Yeah. So I won't go into the definition, but the key input in this construction is this vector space V, which is two-dimensional, has a basis B plus and B minus. This is in degree equals 1, and this is degree equals 2. Okay, and then you have these multiplications. So you have a multiplication from V times V to V, and it's like V plus tensor V plus goes to V plus, V plus tensor V minus, and V minus tensor V plus goes to V minus, and V minus tensor V minus goes to 0. Okay. And then there's the co-multiplication, which is V goes to V tensor V, which sends V plus to V plus tensor V minus plus V minus tensor V plus, and V minus goes to V minus tensor V minus. Okay, so this comes from some kind of TQFT, so this corresponds to this merging perpend, and this corresponds to this like splitting perpend. Okay, so this V straight circle is a V, and then this MF corresponds to the. Okay. So yeah, so Bar Natan has this paper where he generalizes Khovanov's construction, like just looking at the all the algebra with the surfaces you can do, and he classifies all the TQFTs you can use. And the nice thing is that there is in characteristic 2 there is an extra TQFT that doesn't exist in any other characteristic, and yeah, and it works like the following. So, and using that you can construct a deformation of Khovanov homology in characteristic 2 that now I'm going to describe. So I will call it Bn n of L. Okay, and this is going to be a module over f of u over u to the n. Okay, and here, well, remember, Khovanov homology is bigraded, and this u has degree 0 minus 2. Okay, and the chain complex is simply, well, the underlying vector space is the usual Khovanov chain complex, and you tensor it with f of u over u to the n. Yes.
You have to truncate, or you can also have it Bn.
Yeah, you can have infinity.
Okay.
Yeah, you can. Yeah, it's a full deformation. But yeah, we're gonna use the truncated versions.
I see. And
Yeah.
and that exists only in characteristic 2.
Yeah. Well, I didn't tell you yet what the deformation is, but yeah. Yeah. No, this exists in every characteristic, of course. Yeah. But now I'm gonna change the operation. So yeah, that's gonna work on in characteristic 2. So how do the operation change? So here you add a u times minus, and here you add plus u b plus tensor b plus. Okay, you can check, for example, well, these maps, an important property they have is that they have degree minus 1, sorry. So yeah, this thing has degree minus 2, and this thing has degree 1 minus 2. because u has degree -2, so this is still degree -1. And again, here this has degree 1, and this thing has degree 0 because it's 1 plus 1 minus 2, so this is still degree 0. Okay. Yes, so somehow this works in characteristic 2. You cannot leave the signs to z, some miracle. For well, not a miracle, but it's unfortunate maybe. For this case, it works.
Can you say precisely what is it that doesn't work?
I think the signs don't work out in characteristic 0. Yeah.
Meaning that it's not a Frobenius algebra anymore, or?
I don't know. I didn't go in the paper in detail, but yeah, this he says, oh, in characteristic 2, there's this extra thing that doesn't lead to characteristic 0. I guess if you try to work the signs out, they doesn't come in. Yes. Any other question? I don't know much about homology, I have to say. So.
Both Andrew and I seem skeptical about it.
I feel like it might work out as neat.
I sort of feel that.
Okay, yeah, I don't know. That's what Bar Natan said. I haven't tried to use the signs, but yeah. Yeah. So, okay, anyways. Okay, well, anyways, I'm gonna work over Z2, so that's the important thing, I guess. Yeah, I haven't fixed the signs in Z2. Okay. Okay, my first remark was this only works in characteristic 2, but I'm not skipping. Okay, yeah, I was telling you about the thing about the spectral sequence from Khovanov homology to Lie homology. But if you think about that, only works only over characteristic non 2. Because when you diagonalize the TQFT, you have to divide by 2 at some point, right? Do we agree? So, yeah, so if you set, but the nice thing is that Turner showed that if you set u equals 1 here, you get something which is not graded anymore. But that's the right, you get u over f. So you get a TQFT which you can diagonalize over f2, and that you can run the same thing as the homology. So you get you can show that the homology is just the numbers 2 to the some number of surfaces, essentially. Okay, so this kind of theory has been studied a little bit before. Okay, okay, let's call it remark. Okay. Any question? Any other question about this Bar Natan invariant? Okay. So the main theorem I want to tell you about today is the following. So, so there exists a spectral sequence from Bn2 of a link, and which converges to so the 2 pages Bn2. And this converges to HMI y tilde of and here I have to put a reduced version that this means reduced. Okay. Yeah, and setting. So recall this is a module over fu over u squared. Little u, and this is a module over fq over q squared. And indeed, if you set u equals q, you get it's a special sequence of q squared module. Right? So you get this version also happens Q action. Okay, so I'm gonna, okay, as an example, if you pick the triple knot, well, the n you can compute it to be, so this is the homological grading and the quantum grading, -3, -2, -0, 1, -1, -3, -5, -7, -9. So there's one here, there's one here, and there's one here. Okay. So usually something like this, but then you get there's also this U action in the Bar Natan source. And then if you look at the branch double cover, well, sigma of k, well, we know this is an L space. This is by Ozsvath-Szabo. And furthermore, this has the H2 has 3 elements. What's up?
Nothing.
No. Is yours? No.
I mean, it is just L3 once. It's not.
L3-1? Oh yeah. It's a land space. Okay. It's a land space. Land space. And this is due to one. Okay. Then okay. Okay. Yeah. So you have 3 thin C structures, and there's an involution on it. So well, you can guess. So there's one with S equals bar, and then a pair. Let's go to 0. S1. Okay, so that you have 3 elements, and one goes to itself under the conjugation, and the other 2 gets exchanged. Okay, this is the spin structure of the thing. Yeah. So in general, this is a null space, and you can compute it. The Floer homology is rather simple to compute. In particular, in this is going to be the same as the homology of S3. So this contributes to something like this, and this contributes to something like this. Okay, so whenever you have a null space, a pair of of conjugate spin structure which are different gives you an F plus F, and if you have a self-conjugate one, you get an FQ over Q squared. So you can see that, at least in this simple example, the spectral sequence exists. Okay? Okay, so in particular, here you have spectral sequence, converges at the YouTube page. Collapses, as it were. Okay, so now I want to convince you that this spectral sequence exists. So,
Are you using 2 copies of F in that?
what, sorry?
Should there be 2 copies of F in quantum degree -7 in that?
Sorry? What?
Should there be 2 more copies of F in that table for the trefoil image? There is.
No, it should.
There shouldn't. What's going on?
I mean, so he's got a spectral sequence that looks like 2 copies of the
2 copies of
the reduced homology, but then there's a differential, which is basically the Turner differential between the things in degree, homological degree -2 and -3, so that, which is that -7 degree that you're looking at there. So those get canceled.
Yeah, so I guess, yeah, this Khovanov fits in 2 copies with the usual Khovanov. Yeah, there's an exact triangle with this and 2 copies, but there are some differentials in the map, so I guess that's...
Alright, so this is the final page of the spectral sequence.
no, this is the 2 page. The 2 page fits in the, yeah, so there's an exact triangle.
There's a spectral sequence starting in 2 copies of reduced Khovanov and going to his thing.
Yeah, there's an exact triangle.
From his thing to
Right.
So there's an trivial map here, I guess.
Francesco,
Yes.
does this triangle propagate in all pages of the spectral system?
Well, so yeah, there's a triangle, a similar triangle at the end.
Yes.
I'm not sure if homological algebra tells you that there's a, I don't know, probably. I haven't. Yes. Yeah, so this, because this comes from the fact that the group is filtered, yeah, you have a simple filtration, and I don't know, it's probably. Okay. Okay, so 3, it's white words. Okay, let's see. Let's put, well, unfortunately I just erased the TPFT. But yeah, so this is the Khovanov side. And this was the Floer side. Okay, well, let's rewrite the TPFT. So you have V tensor V. To V. Well, I'll just write this bit. V plus V minus V minus goes to 0 plus V minus, and then I have V into V. And this here had a V minus. Okay, so now what's the main difference between Bar Natan's TPFT and Khovanov? Well, there are many, but I think the most interesting from our point of view is like, suppose you have like a splitting coordinates like this, followed by a joining coordinates. Okay. So in Khovanov, well, let's see where V minus goes. V minus goes to, well, it's splitting, so it goes to V minus tensor V minus. And then in Khovanov's TPFT, V minus tensor V minus goes to 0. So this goes to okay. But in Bar Natan, V minus, well, it still goes to V minus tensor V minus. But then V minus tensor V minus doesn't go to 0, it goes to U V minus. So in particular, and you can also check that with the same thing, V plus goes to U times V plus. Okay, so this composition of pseudometric coordinates gives you multiplication by V. So this is okay. Yes. So what's the analog in the Floer side? So on the Floer side. Okay, so what you're gonna do, what you have to check on the Floer side, you take a branch level cover of this. So if you take a branch level cover, that's a standard torus. So the branch level cover is an S2 times S2. So let's call this surface sigma. Oh no, it's sigma, S. The branch level cover is an S2 times S2 minus 2 balls. Okay, so this, well, on this side you have an S3, on this side you have an S3, and then the stuff in the middle becomes an S2 times S2. Yes, and the fact that this map is 0 in Khovanov homology, it's the same thing as saying that the map H, well, I write the H of hat of S3 going to H of hat of S3. The map induced by S2 times S2 minus 2 balls is 0. Okay. Well, whenever indeed this is about much more general. If you have in Heyer's Floer homology or monopole Floer homology, if you have a coordinate which has B2 plus equals 1, because well, you can do it. Well, for example, this map has degree minus 1, so you cannot have anything. So well, remember this is just. But I guess the deeper explanation is that B2 plus of the coordinates is bigger or equal than 1. So the map in the infinity version are 0. Okay, but the important thing is that in the pin2 story this is not true. And indeed, HMI of S3, well, we recall this was f of q over q squared. And the map here, well, is again q over q squared. This is a multiplication by q. Okay, and this, when you go on this side, corresponds to the fact that in Bar Natan theory, the composition of this thing is multiplication by u. You said q equals u. Okay, so this is why this pin2 story adds up. Okay. Okay, so well, I guess this is the key point of the thing, so I want to prove it. This is going to be a short gauge theory introduction. But yeah, do you have questions about this? Yeah, but this is ultimately the reason why Bar Natan's T50 arises in this story, because this map is not zero anymore. Okay. So proof. Well, sketch. Idea of proof. Yeah, so I was telling you, well, this is the same even if you are in the in the pin2 story. It has tilde equals for q over qq, and the map is given by multiplication by q. Okay, and this is geometrically cleaner, so I don't want to talk about this setting. Yes, so essentially, as I was telling you, you should think of q over qq. This is the homology of RP2. And how does RP2 arise in our setting? This is because in a spin structure, the Dirac operator is quaternionic. Okay, so it commutes with the natural involution on the bundle. So okay, the most interesting case, so suppose we are in the case like B2 plus equals 1. So for example, the case we're actually interested in, S2 times S2. Then what happens is like, okay, of course you have to look at the natural thing that you have to look at is the kernel of the Dirac operator. And this is, in the simplest case, actually the interesting case, is the case in which it is non-trivial and has the smallest dimension. But in that case, it's quaternionic, so it cannot be just C, it has to be H, okay? Because the kernel of a quaternionic operator has to be a quaternionic vector space, so in the simplest case, it's H. And the object you have to look at in monopole Homology is the projectivization. And this is just, well, this is a C2. So the projectivization is just CP1, which is S2. Okay? And then you have this action, which is then.
Why do you have to look at this?
Yeah, I won't tell you, but this is what you have to look at. Yes. J. Okay, so the modular space you look at is this S2, which is the projectivization of this, and has this action of J. But yeah, the other thing is that your manifold has B2 plus equals 1, so you have also an R here coming. This is, you should think of it as the co-kernel of B plus D star. And here the action of J, so this is the antipodal. And this is x goes to minus x. And yeah, so this is essentially, this if you look at the picture, this tells you that the moduli space is obstructed in codimension 1. So you have this co-kernel there. But yeah, so what you do is like perturb the equation a little more with an equivariant map. But this, if you think of it, you have this map from S2 to R, which is the antipodal here, and send x to minus x. So this is the same as the tautological bundle over RP2. Okay, that's where how RP2 comes in. And if you pick a section, that's going to be your actual moduli space. So, well, you pick a section of a tautological, and the zero set is Q. Okay. So essentially, the first deformation class of gamma 1 is Q, and it's, well, zero set of a section is Q. And that's why the map there is Q. So it's about the tautological bundle of RP2 in that. So this is actually the moduli space you're interested in. Actual moduli space. Okay. If it didn't make any sense, then okay. But yeah, I just want to tell you why topologically this Q comes from this RP2, which is the moduli space, and you have this obstruction bundle, and the zero set is.
Are you solving the Seiberg-Witten equation in dimension 3?
No, in 4. Dimension 4.
4?
Yeah. This is on the converges.
So A is the trivial flat connection, is that?
Yeah, the spin structure has the spin connection. Yeah.
Yes.
Mm-hmm.
And, okay, so you're saying that the Dirac operator does have this two-dimensional kernel.
But also, but the equation also have a co-kernel, which is one-dimensional because of the B2 plus equals 1.
Mhm.
And then when you see perturb, you see the generator of the first homology of RP2 as your moduli space. If you do equivariantly, that's the important thing.
And so I don't know, I mean, you write S2 goes to R.
Yeah, sorry. So you should think of it this is the kernel and this is the co-kernel.
Yes.
So to find the actual moduli space, you need to find a map to perturb this equation a little more. And that's the same as taking a section of the tautological on RP2. Yes, and the zero section then is this Q that arises in this stuff. Is it clear?
Not quite. So like.
Yeah. Okay. The trick is that.
So is the R giving me a bundle over S2 or is it?
Yeah. Well. Okay. No. This was very sketchy, so it doesn't make sense. So nothing makes sense. But this is. Yeah. The important thing is that you're doing it equivariantly, because if you allow non-equivalent things, then you can just perturb it away. And you see the usual thing that's on B2 plus equals 1, the map is 0 on the reducible. But yeah, requiring that this map is equivariant tells you that thing descends to RP2. Mm-hmm. So then you see this Q coming out. Yes. So yeah, as a remark, so yeah, this fact that essentially this idea was already in. In Kramer's proof of Donaldson theorem B and C, so this extends D. So Donaldson theorem A was like negative intersection form, it's standard. Donaldson theorem B was if X is spin and plus B2 plus equals 1, then it has the intersection form of S2 times S2. Okay, so if you have a spin manifold with a small d1, then it has to be S2 times S2. And this extends, well, the same argument extends for manifolds with boundary in terms of Manolescu's correction terms also become gamma. Okay, in the same way, like the D invariants extend Donaldson theorem A to manifold with boundary. Probably short way. Okay. So yeah, this argument was already it's in a talk by Cronheimer and it was never published. Talk by Cronheimer from the early 90s. Okay, so now I'll switch to why it does not work in the things. Okay. Yes, if you remember at the beginning, I told you the two key ingredients to prove this spectral, to prove the existence of these spectral sequences are first, well, the things on S2 times S1 or have to be the right ones, and this works. This was the why it works. And the other thing was the Montesinos trick. So when you go to the branch level cover, you have these surgery things, and so you want your surgery exact triangle to work well. Yeah, and that's the thing that doesn't work well in the P2 story. Why it does not work in P2. Okay, so in P2, the same argument, the same statement. So there is a natural spectral sequence, but at least I don't know how to show convergence at the moment, and this is the reason why. Okay, so recall there's a surgery exact triangle. So suppose you have a knot in a free manifold, and you have gamma I for I equals 1, 2, 3, which are framings for which gamma I times gamma I plus 1 equals minus 1 framings. Okay, so from these you can construct these new three manifolds of Hilbert surgery, and yeah, Khovanov, Ozsvath-Szabo, they show that there is surgery exact triangle. Okay, these three manifolds fit in an exact triangle. Okay, yes, but it's actually cooler because these maps, there is a natural to handle attachment from yi to yi plus 1, which I call wi. And these are actually the maps induced by those cohorts. One, two. Okay, so it's all very natural, all very good looking. In the Pin2 case, the thing is much messier sometimes. So, theorem. In the Pin2 case, you have the tricky part is that exactly two of the WIs are spin. Okay. Without loss of generality, you can say W1 and W2. And the surgery of the triangle looks like the following: HS, Y1, HS, Y1, 2, HS, Y2, and here HS, Y2, Y3. And here there's another map that's it's unclear what it means exactly. It comes from, well, the algebra of the problem spits out this map. And yeah, and if you actually put the usual map, you get something which is not where the map doesn't even compose to 0. So there's a problem. Yeah. So for example, well, the simplest example of this fact is like if you take the unknot inside S3. Well, the mad things you see are like S3, S2 times S1, and S3. And this cohort is S2 times 2 minus the ball, which is spin. That's 2 times CP2 minus the ball, which is also spin. And then here you get a CP2 bar minus 2 balls, which is not spin. Okay, so these you keep and this you throw away, but algebra gives you another map to fit in, and that fits in the section. Okay, so the problem with proving the thing in the pin2 case is exactly this, that your exact triangle is not that natural because you have this third cobordis map, which is unclear what it is. So I don't really know how to prove in the pin2 case, but miraculously it works in the involutive case. So that's why the theorem works, and the idea is the following. I'll just end on this. Yeah, so okay. So the important thing is the following. So the blow up formula. Okay. So in the monopole case, or in Heger-Floer, the map associated to if you have this and you blow it up, this is 0. Okay, because you have on CP2 you have all these conjugate species structures and they cancel, at least over Z2. That's what I'm thinking about. Okay, but in pin2, this is not 0. Okay, so that's the issue because in the surgery exact triangle, when you compose 2 consecutive coordinates, you get something which is a blow up or something. So this fact. The composition is 0 in the usual case because this map is always 0. And in the pin2 case, this is not true. But the nice thing, you can always write it as it's q squared times something x. Okay? So in pin2, q squared is not 0, but q cubed is 0. And the issue here is that this is not 0, but q squared. So in particular, if you set q squared equals 0 formally, which is the same as going to the involutive version, in HMI, here this is a module over f of q related to cos over q squared, and there the action of q squared is 0. Well, this map is 0. Well, there is hope at least. Okay, and all the technical work is to show that this actually follows at the chain level, and you can do all the surgery triangle machinery on it. But this is ultimately the reason why the theorem, at least I can prove over for this group, and I can prove for this group. And I guess.
So where's the involution?
So
Actually, what I really want to know is where the involution is in the Bar Natan story.
Oh yeah, that's unclear to me. Yeah, I don't know. It's somewhere hidden. Also at the spectrum, it will be interesting to understand this at the spectral level where this involution is. But yeah, I don't know. Yeah.
So you don't expect that it exists at the chain level.
But it's weird because the evolution, the action goes down in the quantum gradient, not in the homological gradients in some sense. I don't know. I don't know where the evolution is in the Khovanov story. Yeah, that's an interesting problem, I guess, to find.
Can you say what the spectral sequence looks like for T35?
T35. I think we did a computation once with Leon, but I guess. But the branch level cover would just be like you have a Q because it's a null space, so you get this Q, and then you have some cancellation there, which is interesting here.
Why T35?
I don't know. I mean, presumably the Turner differential is interesting on the Khovanov homology of T35, so they've got an interesting, Bar Natan's deformation, because the double branch cover of the T35 is the Poincare sphere, so then you'll probably get an interesting spectral sequence from that.
Yeah, so you have a lot of cancellation, I guess. Yeah.
What is the candidate for the spin to equivalence?
Oh, it's BN3.
And what about the other ones?
Oh, the BNN?
Yes.
Yeah, I guess somehow, yeah, I guess Marco pointed out once that on the Floer side, it's really hard to go over Q equals 0 because the K3 surface exists. So you cannot go over like one. So there are spin 3 manifolds with B2 plus equals 3, which is like connect sum of S1, S2, then S2 3 times, and the K3. So Donaldson theorem B and C doesn't have a Donaldson theorem D. So I guess that's it. yeah. So because of that, and that's a counterexample to Donaldson theorem B. So I don't know on the Floer theory side how one will get the higher Q, the higher B and N's. Yeah, that's.
Can you explain why this blow-up formula? Where the
Yeah, so essentially, it's always about RP2. So this is S2, and you have RP2. Okay, now essentially, if you pick 2 points here, and you quotient 2 antipodal points, the quotients, and they give you a generator of RP2. Okay, and these are the moduli spaces in the blow up coming from the spin C structures of CP2. And yeah, so these pairs of modular spaces which are 0-dimensional in each critical submanifold will give you this Q square coming out because of this. Q square is the generator of the point in RP2. I guess. Yeah, while in the usual case, these 2 points cancel in the homology of S2 because they're both generators of the homology of S2, so they cancel. But once you go to RP2, they became the same points, so they generated homology, so they don't cancel anymore. I guess that's the moral. So it's all about counting mod 2, essentially, but you divide by 2 before. So.
And I mean, like if you were to work over Z in the original spectral sequence, you'd find yourself thinking about odd Khovanov homology. I realize that the ring structure is not as good, but I mean, is it possible that this sequence also works over Z?
Yeah, I don't know. I haven't thought about it. Yeah, but yeah, that's a very if you can find a odd Bar Natan deformation, kind of something like that. Yeah, that's. Yeah. Of course, you lose this action because then at least in the.
All right, let's thank Francesco again.